Hello, in this video, we're going to explore a fascinating topic in combinatorics called Ramsey Theory. Specifically, our goal is to prove a classic result known as the Ramsey number R, 3, 3. This might sound intimidating, but by the end of this video, you will be able to understand the core concept of Ramsey numbers and independently prove that R, 3, 3 is equal to 6. So, what exactly is a Ramsey number? Let's start with a simple idea. The Ramsey number RST is defined as the smallest number of vertices, let's call it n, in a complete graph such that if you color the edges of that graph with two colors, let's say red and blue, you are guaranteed to find either a complete subgraph of size S with all red edges, or a complete subgraph of size T with all blue edges. Let's break that down. A complete graph means every vertex is connected to every other vertex by an edge. Coloring the edges means assigning one of two colors to each edge, like red or blue. The Ramsey number tells us how many vertices we need to guarantee that a specific pattern emerges, no matter how we do the coloring. It's a statement that complete disorder is impossible. In this video, we are specifically interested in R, 3, 3. So, in our case, S equals 3 and T equals 3. R, 3, 3 is the smallest number of vertices in a complete graph that guarantees we can find a triangle where all three edges are red, or a triangle where all three edges are blue. We call these monochromatic triangles. A K_3, or a complete graph with three vertices, is just a triangle. So R, 3, 3, is the smallest number of people at a party such that you can always find three people who are all friends with each other, or three people who are all strangers to each other. Edges are relationships. Vertices are people. Our objective is to prove that R, 3, 3 equals 6. Proving this number has a specific value usually involves two parts. First, we must prove that the Ramsey number is less than or equal to 6. This means we must show that with 6 vertices, a monochromatic triangle is always guaranteed. Second, we must prove that it is strictly greater than 5. This means we must show that it is possible to color a graph with 5 vertices without creating any monochromatic triangles. This is called a counterexample. If we can prove both of these statements, we have successfully shown that the Ramsey number R, 3, 3 is exactly 6. Let's tackle part 1 first. So, let's start with part 1, proving that R, 3, 3 is less than or equal to 6. We'll use a technique called the pigeonhole principle. It's a very intuitive idea. Imagine you have more pigeons than you have pigeonholes. If you put one pigeon in each hole, at least one hole must end up with more than one pigeon. Now, let's apply this. Consider a complete graph with 6 vertices. Let's call them V1, V2, V3, V4, V5, and V6. Pick any one of the vertices, say vertex V1. This vertex has 5 edges connecting it to the other 5 vertices. We are coloring each of these 5 edges either red or blue. Now, here's where the pigeonhole principle comes in. If you divide 5 by 2 and round up, you get 3. This means that at least 3 of those 5 edges must have the same color. There's no way to color 5 edges with 2 colors without having at least 3 of one color. So, we've shown that there are at least 3 edges of the same color emanating from V1. Let's explore the consequences of this. We've established that at least 3 edges from vertex V1 are the same color. Let's imagine, without loss of generality, that they are all blue. Let's assume there are 3 blue edges from V1. Let's say they connect V1 to vertices V2, V3, and V4. These 3 vertices form what we call a neighborhood of V1. Now, consider the 3 edges that connect these 3 neighbors of V1, V2, V3, and V4. Let's call the vertices V2, V3, V4 our triangle of interest. There are 3 edges within this triangle of interest, V2, V3, V3, V4, and V4, V2. Each of these edges can be either red or blue. Think about edge V2, V3. What color is it? If it's blue, then we have a blue triangle formed by V1, V2, and V3. Our mission is accomplished. But what if the edge V2, V3 is red? We don't have a blue triangle yet. Let's keep looking. What about edge V3, V4? If it's blue, then the triangle V1, V3, V4 is blue. Mission accomplished again. And what about edge V4, V2? If it's blue, then the triangle V1, V4, V2 is blue. Mission accomplished. What is the only scenario where we do not find a blue triangle? It's if all three edges in our triangle of interest, V2, V3, V3, V4, and V4, V2, are red. But if they are all red, then the vertices V2, V3, and V4 form a red triangle. Our mission is accomplished this way instead. This covers all possibilities. Either one of the edges connecting the neighbors is blue, giving us a blue triangle, or all of them are red, giving us a red triangle. Either way, we are guaranteed a monochromatic triangle. And this proves the first part of our statement. R, 3, 3, must be less than or equal to 6. This concludes part 1 of our proof. We've shown that R, 3, 3 is at most 6. Now for part 2, proving that R3, 3 is strictly greater than 5. To do this, we need to show that a counterexample exists. That is, we need to draw a complete graph with 5 vertices, k_5, and color its edges with red and blue in such a way that there is no monochromatic triangle. If we can find such a coloring, it means that 5 vertices are not enough to guarantee a monochromatic triangle, and thus the smallest number of vertices that does guarantee it must be greater than 5. Let's draw a complete graph with 5 vertices and arrange them in a circle. Each vertex is connected to every other vertex. Now, let's assign colors. Let's color the edges of the pentagon itself blue. These edges are 0, 1, 1, 2, 2, 3, 3, 4, and 4, 0. This creates a blue 5 cycle. Notice that this coloring does not have any blue triangles. Why? Because you would need 3 consecutive vertices connected by 3 blue edges, but our cycle only connects adjacent vertices. Next, let's color all the remaining edges red. These are the edges that form the stars or the diagonals of the pentagon. 0, 2, 1, 3, 2, 4, 3, 0, and 4, 1. This creates a red 5 cycle. Does this coloring have any red triangles? No, for the exact same reason as the blue cycle. You need 3 consecutive vertices for a triangle, but the red edges connect vertices that are next but 1 to each other. Therefore, we have found a valid 2 coloring of k_5 that contains no red triangle and no blue triangle. This is our counterexample. It proves that R, 3, 3 is greater than 5. Let's bring it all together. We set out to prove that the Ramsey number R, 3, 3 equals 6. We accomplish this in 2 critical steps. First, we use the pigeonhole principle to show that in any 2 coloring of a graph with 6 vertices, you are absolutely guaranteed to find a monochromatic triangle. This established that R, 3, 3 is less than or equal to 6. Second, we found a specific coloring for a graph with 5 vertices that contains no red triangles and no blue triangles. This proved that 5 vertices are not enough, meaning R, 3, 3 must be strictly greater than 5. By combining these 2 results, we get that R3, 3 must be exactly 6. We have successfully proven that the smallest number of people you need at a party to guarantee 3 mutual friends, or 3 mutual strangers, is 6. Today, we learned the definition of Ramsey numbers and used a 2-part proof strategy to show that R, 3, 3 equals 6. You are now able to explain and prove this fundamental result in combinatorics. I hope you enjoyed this journey into Ramsey theory.